Hello everyone, I'm Akshita. I'm here to briefly discuss about hazards and combinational circuits. To begin with, what is hazard? Hazards are unwanted switching transients that may appear at the output of a circuit. Switching transients are nothing but abrupt change of state. These transients occur when different paths from input to output have different propagation delays. A hazard is a condition in which a change in a single variable produces a momentary change in output when no change should occur. Let's move on to the types of hazards. There are three types of hazards. Those are the static hazard, dynamic hazard, and the essential hazard. Essential hazards can be seen in sequential circuits. So when we discuss about the combinational circuit, we can see only the static hazard and the dynamic hazard. So static zero hazard. In static zero hazard, the output temporarily changes to 1 when it should have stayed to 0. In static 1 hazard, the output temporarily changes to 0 when it should have remained at 1. In dynamic hazard, the output changes multiple times when it have made a single logic transition, that is either from 0 to 1 or from 1 to 0. These figures show possible outputs from a circuit with hazards. In each case, the output of the circuit is correct, but due to some switching transient appearing, the circuit output changes when the input is changed. So here in static zero hazard, we can notice that the output should remain at 0 for any of the input, but due to the propagation delay, it raises to 1 and again it reaches to 0. In a similar manner, in static 1 hazard, the output should remain at 1, but due to some switching transients, it lowers down to 0 and again it raises to 1. In dynamic hazard, it changes from 0 to 1 and again it changes from 0 to 1, which should have appeared only once. Here the multiple transition occurs. So let's move on to the difference between the static and dynamic hazard. So static hazard occurs when an input changes and it causes the output to change at the same moment before output becomes stable. But in dynamic hazard occurs when output changes for two adjacent inputs while the output should change only once. Static hazard occurs in combinational circuit. Both static and dynamic hazard occurs in combinational circuit itself, but dynamic hazard occurs in a multi-level circuit. Static hazards are easy to resolve, but dynamic hazards comparatively is complex to resolve. Static hazards can be eliminated by using redundant gates. Dynamic hazard can be resolved if we are able to cover the static hazards. Static hazard causes temporary false output value. Dynamic hazard results in a transition of a wrong state. So I'll be discussing about the static zero hazard and dynamic hazard in a depth. If we know about the static zero hazard, then it is a bit easier to understand static one hazard. So in my explanation, I'll be going into a depth of static zero hazard and their covers. So what is static zero hazard? As I mentioned before, the output should remain at 0, but due to some unwanted switching transient and as we change the input, the output momentarily changes to 1 before setting on to 0. In properly two-level AND or gate, we don't see the static zero hazard. That is in the sum of products expression, we don't see the static zero hazard. Static zero hazard doesn't appear there. But in a product of sum expression, that is in OR and implementation, static zero hazard occurs. So this is a circuit, this is a condition where we can see the static zero hazard. So here AA dash is the basic condition which generates the static zero hazard. So consider I'm giving a input A to be 0. So the 8 bar will be 1. So 0 1, the output of AND gate will be 0. Now, if I change this A to 1, the NOT gate should NOT gate output should change to 0. But due to the propagation delay of NOT gate, it doesn't immediately change to 0. It remains at 1. So due to this 1 and 1 condition of the A input, the output will change to 1. So here we can see we wanted only the 0 as the output, but due to the propagation delay of the NOT gate, we are expecting 1 at the output. So which should not have been occurred. So we can see there are two ones appearing, and hence the output of the AND gate will be 1. So this is the basic condition where we can see the static zero hazard. So this is a timing diagram illustrating the static zero hazard. So as I showed in the previous slide, if I give the A output to be 0, A bar will be 1 and the final output will be 0. Now if I change the A input to be 1, A bar doesn't change to 0 immediately. It remains at 1. So this output can be seen here. So 1 1 will have the output of AND gate to be 1. So a glitch has appeared here due to the NOT gate delay. That is, the tau is the NOT gate delay. So due to that, we are able to see the glitch which should not have been occurred. So let's take an example, that is a circuit with static zero hazard, and try to cover that. So this is a simple example, simple circuit where we can understand the static zero hazard. So consider when you solve this circuit, we'll get the expression as this. So I will consider the A input to be 0 and even the C input to be 0 always. Now initially I'll consider B to be 0. So let me see what output we get. So as A and B is 0, this is the OR gate. The OR gate output will be 0. But this is the B bar thing. So due to NOT gate, here it will be 1. So 1 plus 0 will get 1. So 0 and 1, the output is 0. So this is fine. But when I change this B input to 1, A and C remains, I'm not changing A and C, it will remain 0 itself. But when I change this B to 1, the NOT gate, it will have some propagation delay, and due to that, it will not change to 0 immediately. So due to this will be 1 only, and here I have changed B to 1. So this output of first OR gate will be 1. So 1 1 conditional we have got, and hence the output changes to 1. But so here we can see the static zero hazard condition. So this is just the K-map plotting of the represented circuit. I have just plotted this expression. So this is nothing but A and this is B and C. So here the condition is 0 0. So I think you should be knowing the K-map representation thing and how to plot an expression in the K-map. So let me show this example once so it will be clear. So A plus B, that means here in product of sum expression, the max terms we have is 0 1 and 2 6, and 0 is the variable and 1 is the complement. So this term expression will be A plus B, common of these two, and B bar plus C will get through this. So this is just I have plotted the K-map expression in the K-map. So let me see how to cover this static zero hazard. So the most commonly used method to eliminate the static zero hazard is to add the redundant logic. So Just write down the product of some expression for the circuit, then plot each term on the map and loop it. We can eliminate the zero hazard by looping additional prime implicants that cover the adjacent zeros that are not already covered by a common loop. So let me take the previous example and tell you clearly. So here in that expression, this is the A plus B, and this is nothing but B bar plus C. And here we may notice that even the cell 0 and 2 are adjacent to each other. As mentioned in the step, we have to loop the adjacent cells. Okay, so when we fold this K map, we may see that even the 0 and 2 have a 1-bit difference, and hence we should loop this also. So when we loop these two terms, we get the expression A plus C. So if we include this term in our final expression, then we'll able to remove the static zero hazard. So let me explain you. So I told you that I'll be considering A plus A and C has 0 always. So if I include this A plus C term in my circuit, so for any value of B may be anything, like I can change B to 0, B to 1, and let there be any propagation delay in the NOT gate. It doesn't matter to me now. So as A and C is 0, I have included the OR gate of that. So this output will always be 0. And if any one of the input to the AND gate is 0, then the final output will always be 0. So we can, here we, our expectation is satisfied that there is no static zero hazard appearing, because we won't get 1 at the output. We always get 0. So, but we may notice here that due to the static zero hazard, to cover that, we are adding one more term in our expression. But our intention is only to eradicate the static zero hazard. So, in order to cover the static zero hazard, we have added an additional term. I hope you have understand the static zero hazard and it's covered properly. So, let me move on to the dynamic hazard. Dynamic hazards occur in a multi-level circuit, as I told you before. So where the output should change 0 to 1 or from 1 to 0 only once, but it occurs multiple times. So the output of logic equation, as I told that A dash is a final expression that condition where static zero hazard occurs. The same way dynamic hazard occurs in this condition, that is y is equal to A plus A bar A, or you may have this condition y is equal to A plus A bar whole bracket of A. Dynamic hazards are more complex to resolve, but we may note that if all static hazards are eliminated, then eliminating dynamic hazard is much bit easier. So this is the circuit where we can see the static one hazard also, which that it is an implicit static one hazard, so due to which dynamic hazard occurs. So static, as I told you that A bar is a condition for static zero hazard, and the dynamic hazard expression also I've told. So this is the condition of static one hazard. Here the X path have 3 conditions to be satisfied. You may notice this. One here, and this is the direct expression where we can see the static one hazard, and this to this the other path of the x goes, and this in this path there will be more delay of x. So due to this condition there will be a dynamic hazard. So the static one hazard, the glitch appears here, you may notice this, and due to this glitch and due to the delay of the x term, that is the input term, we can see the dynamic hazard appearing. Let me consider this circuit with dynamic hazard and explain it in a detailed manner. So when we solve this circuit, we'll get this expression. So I'll consider initially the A, B and D is equal to 1. So this expression reduces to Y is equal to C plus C bar into C dash. That is nothing but C bar. So this is the basic condition of dynamic hazard as I told before. So here the C is the variable which is causing the dynamic hazard. All other A, B and D is just constant. I'm not changing its value. So let me explain this with using the timing diagram. Here y1, y3 and y2 are also the it's the output of the NAND or and AND gates. So let me consider initially the C to be 1 and y1 is nothing but, so let me write down here everything is 1. So y1 inputs are C and D as you can observe here, and C is 1, D is 1, so output of y1 that is a NAND gate will be 0. Y2 is nothing but A and C. A and C is 1, 1. So output of Y2 will be 1. Y3 is nothing but B and Y1. That is Y1 is already 0 and hence Y3 will be 0 due to the AND gate we have, that 0 condition. And Y4 is the OR gate. So Y2 is already 1. So hence Y4 will be 1. The final output Y is Y4 and Y1. Y1 is already 0 and hence the condition we have, the final output will be 0 itself. Now if I change this C 0 to 1, Y1, let me see what happens. So Y1 was, so this has become now 0. So CD, that is 0, 1, we should have the output Y1 to be 1. So that occurs after some time tau, and this Y2 is 1 and 0, that is 0. So that appears here after time tau, and Y3 is 1 and this is 1 and 1 and 1, that should appear 1, so that appears after time 2 tau, we can see here. And Y4 is, here the condition 0 appears and here also it is 0 and that should go to Y4 will be 0. So this also appears after 2 tau seconds. So here it is the glitch which we can notice the static 1 hazard, and the final output Y, it should, so due to this glitch happening, it changes from 1 to 0 and again from 0 to 1 when you give some when you see the later conditions. So this appears in time 3 tau. Here you can see that Y is nothing but Y4 and Y1. So Y1 it is 1. So 1 and 1 it raises to 1, this condition. But later due to this glitch happening, it again falls to 0 and again has the static 1 hazard raises to 1 output. So it becomes 1, the final output. So the multiple transition can be seen here. So this is a condition, this is a circuit example where we can see the dynamic hazard. So how to overcome this dynamic hazard? Transfer a multi-level circuit into a two-level circuit. Eliminate all of the static hazard as I mentioned before. So this is the previous example which I've taken. So in order to prevent the dynamic hazard to occur, first the basic thing is we should cover the implicit static one. So how can we do that? By adding AB. If we add the AB to the expression, then we can cover the static one hazard. As I told you that I have considered the A, B, D, to be 1, right? So this expression now reduces to C, that is A is 1, so C bar, because B is 1, and this A is 1, B is 1, 1 dot 1 is 1, and there C dash. So we can see here we were observing a static one hazard in the previous slide, but due to we have added this A dot B, we can overcome the static one hazard. So this final expression will be, this will be reduced to 1, right? Because 1 plus anything is, will get the same 1. So that into C bar. So the Y, the final output, will only be C bar. That will get the same thing what we give. The complement of C will get. So by adding, by covering the static one hazard, we can overcome the dynamic hazard in this example which I showed. So in a similar manner, if we cover the static hazard, then we can eliminate the dynamic hazard. So I hope you have understood this dynamic hazard covering thing, because it is very complex to resolve. I have taken the simple example, so you may try out this with the same step with the other examples also. Here we are at the end of the topic. So far we have learned about what is hazard, types of hazards, there are differences between the static and dynamic hazard, and we have gone into depth about the static zero hazard and dynamic hazard, and we have seen their covers, how to recover those hazards also. I hope you have understood and have some clear idea about the topic. Thank you so much for your time and attention.